So let's do there's kind of two irreducibility criteria that I want to talk about. So there's two irreducibility criteria that I want to talk about. The first one, they're both pretty basic, but they're pretty straightforward to apply. So there's two criteria, easy to apply criteria. For determining if a polynomial is irreducible. Okay, the first one is testing mod a prime ideal. So the first one is reduce mod a prime ideal. And the second one is this thing called the Eisenstein Irreducibility Criteria. Okay, so let's do this first one so it's easier. So so I guess we could call this is maybe a non-standard thing, but there's a reduction test. Okay, so what we'll do is we'll let f of x be an element of R of x for R a domain, say. I don't think that's necessary, but let's just be safe right now. Okay, so for R domain, and so let P be a prime ideal. This also really isn't necessary. I think you can do it for any ideal, right? And so if f of x mod P in here, and so we should do R mod P of x is irreducible, then so is f of x. Okay. Oh. Okay. So so the proof goes like this. It's by contrapositive, right? So if f of x is equal to g of x, h of x, then I guess maybe we need here that. Okay, well, let's do it like this. If f of x is equal to g of x, h of x, then f of x bar is equal to g of x bar, h of x bar. But if this is impossible, right?
Did you maybe mean to say reducible? No.
Irreducible. So you can test irreducibility modding out. So like if you have a factorization, so what I'm proving here is that if it's factorable, so if you can factor it, right? I'm proving the contrapositive. If you can factor it, then you can factor it mod P, right? That's what I'm proving. Yes, but if such a factorization exists, then then or doesn't exist. Sorry. Oh, I was trying to like erase with my finger. So if such a factorization exists, then I mean, I guess this is the this is the contrapositive right there. Sorry, it's just that easy. I don't even know what I was saying. So the converse is if you can't factor, right, then you can't factor in the top. Okay, so let's do like an application. Okay. All right. So consider this polynomial f of x is equal to x squared plus x plus 1. Of course, you could you could test this, since this is a quadratic polynomial, you could test this by just using the quadratic formula and factoring and seeing if those factors are integers, right? But I'm going to pretend like we don't know how to do that and do this proof in another way, right? Okay, so what we'll do is we're going to reduce this mod p. So reduce this mod 2. So mod 2. So we have this thing. So f bar of x, which is x squared plus x plus 1. So this is in f2 of x. Okay, so that's we reduce the coefficients mod p. But we have that f bar of 0. So this is 0 plus 0 plus 1, which is 1. And f bar of 1 is, so this is 1 plus 1 plus 1, which is 1. So this is 1 mod 2. Mod 2. So this proves that f of x has no roots. F of x bar has no zeros in f2 of x. And hence is irreducible. Okay, and that implies that f of x, the original f of x, is irreducible. Okay.
Could you maybe just say why that's good? I know it's the idea, but why that's good enough? Like, why don't we need to check 0, 1, and 2 for mod 3?
It's good enough because of the theorem, right? Because if you reduce mod p, that's good enough. If you have a factorization, then you'll have a factorization mod p.
Oh, just for a prime ideal.
Yeah.
Oh,
I think there's one thing that I'm worried about here is maybe you need a hypothesis. So let me just put this here. So maybe there's a hypothesis. On f bar of x in r of x or rp of x being non-zero or something, or having the same degree. I don't exactly remember, but it seems like that this proof just works, right? So if you have a factorization here, then you have a factorization in the reduction, and hence on the so the contrapositive, right, says that no factorization. So no factorization mod p implies no factorization. Okay, so this statement is that there exists some. So this is that there, if this is like there exists a g and there exists an h, and then this is saying then there exists a g bar and there exists an h bar. And then this no factorization, of course, is so this no factorization statement is really saying, for all g and h, that f is not equal to g times h, right?
I wonder if Keith was thinking what I was thinking. Is like I'm used to thinking like for all p, but if you don't have the other one, if it's reducible for some p, that does not imply that it's reducible.
No, exactly. The other way, that's true, right? So that's the thing that you have to worry about. So just because it factors, if it factors mod p, doesn't mean you can lift the factorization. Yeah. Irreducibility is good. Factorization is not good, right? So you can test irreducibility. You can't test whether something factors mod p. Yeah. In fact, factorization mod p like it tells you about the splitting behavior of like prime ideals in number fields. So like, we can talk about that after class if you guys want to hear more about that. But that's kind of beyond the scope of this class. That's kind of one of the theorems. That's a theorem from algebraic number theory.
Is there a theorem like if it factors for all p mod p, then it factors? Is there something like that, or
no? There's actually, I think there's actually examples, and I'm not 100% sure. I don't know one off the top of my head, but I believe that there exists examples that reduce mod p for all p, right? But are irreducible.
Okay, that'd be pretty wild, yeah.
Yeah, they're pretty wild. It gets wild, right? I think you might need more variables than one. I'm not sure. Yeah, I'll look for that after class. Okay, and so you don't need to do mod p as well, right? You could have done something like, okay, so here's another example, right? So let's do, if I consider f of x, y to be x squared plus x plus 1 plus y. Okay, so I'm kind of cheating, right? So if we do this in z of x, y, right? Well, since f of x, y mod the ideal y, that's a prime ideal, is equal to, x squared plus x plus 1, right? And this is in, okay, z of x, let me write it like this, z of y mod y of x. And I'm viewing this as kind of z of y x, right? Then this implies f of x, y. Oh, so since this is this, and we know it's irreducible, this is irreducible in z of x. Okay, so this is really z of x, right? This implies that f of x, y is irreducible. Okay. All right. So
if you had if it was x squared plus x times y, would the y just disappear still when you'd mod out by
plus xy? So if you did this, so this thing, so
if you modulo y, does that y disappear?
Yeah, if I do mod y, this just becomes x squared, and this is reducible.
Oh, just x squared. Okay, thanks.
It just becomes just x squared, yeah. Okay. Okay, so this is kind of the idea for this one, right? And you can apply it to whatever rings you want, right? So as long as you can prove irreducibility mod the ideal. Okay, so let's do the next theorem. So let's do the Eisenstein. Okay, so this one says, so let R be a domain. Okay, and let f of x be this polynomial, a1 plus a1x plus dot 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 plus a n x to the n in R of x. Okay, and so then let P be a prime ideal. Of R. Okay, so then we have some conditions, right? So let's do it like this. So if all the coefficients are divisible by the prime, meaning that if AI is in P, right, for 0 less than or equal to I less than n, strictly less than n. This is important. A0 is not in P squared. So it vanishes to order 1, but not to order 2, right? And then if AN is not in P, then these criteria, so these are the Eisenstein criteria. This implies that f of x is irreducible. Okay, so these are the Eisenstein criteria. Polynomials that satisfy these criteria are called Eisenstein polynomials.
So Taylor, you said kind of at the start of going through these two different ways, these two big ways of determining irreducibility, that the first one is easier. Did you say that? Or is this easier?
I mean, it's easier. It doesn't always apply though. That's the downside. Like, so sometimes you'll have something and then you'll like reduce it mod whatever, right? And that thing's still complicated. And so you're kind of like stuck to where you were originally.
Right. So I guess my question is, like, if you were to try something first,
yeah,
are you trying Eisenstein first?
Does
it will always work?
I don't. So yeah, I don't know. I'd probably try reducing first. So like another example. So let me give another application of this. Okay, let me finish this statement.
Okay, yeah.
Let me finish the statement, then I'll talk about that again. So polynomials that satisfy criteria are called Eisenstein. So sometimes people will talk about Eisenstein polynomials. All right.
On a smaller scale, Eisenstein's nice because you can just see, like, if all the the constants, you can, if you factor them real quick, you can see. It's like, oh yeah.
Yeah, exactly. So like, an easy example. All right, let's just make one up, right? So let's do 2 plus 2x plus 2x cubed plus, I don't know, 4x to the 4th plus 2x to the 5th plus x to the 6th, right? This is an Eisenstein. You could do 2 to the 20 here, say, right? The only important condition is that this one needs to be not, not divisible by 4. So this is in z of x. And then the prime ideal here is, of course, the prime ideal 2 by 4. These things can be as crazy as you want, right? Here, these things can be two-adically as small as you want. And then this one here can be, this one has to be not divisible by 2. Okay. Notice that this is an example where if you reduce it mod 2, right, it's x to the 6th, right? So, this one and our other method are disjoint. Okay, so let's go. Let me just say another thing about this example here. So another thing that you can do back to like what are the easy methods. So like if f of x, so given f of xy in, say, I don't know, f of xy for f of field, and then f of a y, right? So this thing is a polynomial in f of y, but this thing here is also f of xy mod the ideal x minus a, and then this thing is a prime ideal. Right? So you can test irreducibility by plugging in special values and checking. And checking irreducibility there. For that specialization. Does that make sense? So let's see if I can come up with a quick example. So again, I'm kind of worried about the degree. So if we plugged in something for x here, right, then you know, you'd get an irreducible polynomial, but it'd be of degree 1, right? But yeah, so like that doesn't work, right? Because you could have something like, you know, so look at this example. If I took like f of xy to be another example, to be something like, I don't know, g of x times h of y, or not h of y, let's see. Well, I guess that's not irreducible. Oh yeah, let's do it like this. Yeah, that's a good example. G of x, h of y. Okay, so this is not irreducible. Right? But suppose, you know, you could do something like, but after plugging in x is equal to 0, it could be irreducible. But that's bad because it changes, you know, it kills some degrees. So like, so let's see what I mean here. So like, this for concreteness, let's take f of xy to be, you know, x squared plus x plus 1. Or let's make it even simpler. X squared plus 1, y squared plus 1. And then we'll take this to be in Q of xy. Well, f of xy mod f of xy mod okay, so f of xy mod x minus, I don't know, 1, right? So this is equal to 1 plus 1, and this thing is y squared plus 1. So this is 2 times y squared plus 1. And then this thing is irreducible. So what happened here? Okay, so what's the issue with this example here? Well, there's a condition. Okay, and so the condition here, now I remember the condition. If we go back to here, so this is what I was saying up here. So you actually need, so what you need is, so you need f of x to be primitive. Right, meaning, so you can't have common factors. So the coefficients. The idea here is that the coefficients of f of x in R of x need to generate a trivial ideal.
Relatively prime?
Huh?
You mean relatively prime or no?
Yeah, relatively prime. That's the same thing as relatively prime in R. Okay, and so let me look this up. I don't want to, so take this with a grain of salt right now. I'm going to look this up after class to make sure that I'm stating everything completely correctly. Okay, so but there's conditions like this, and this is one of the examples that's bad, is because here, right? So as a polynomial, so here R, so we have this is like Q of x, y. So R here is Q of x. And all the coefficients of this are the same, right? All the coefficients, they generate this ideal x squared plus 1, and that's something that can cause issues, right? Yeah. Okay. So that being said, let me yeah. Okay. I mean, if you knew right away that you could factor something out, then the thing's silly anyway. So, okay, let's go back to this Eisenstein business. Okay, so let me do another example of something that you need to do sometimes. Okay, so, all right, so let's do another example with Eisenstein. Okay, so for g of xy, so consider the same polynomial, right? X squared plus x plus 1 in z of x. So is there a way that we can modify this polynomial to make it so that it's applicable, so Eisenstein is applicable? Yes, right? So what you can do is there's a trick, right? So we can't apply Eisenstein directly. But we can shift it. And this is a really common trick. Okay, so so note that f of x is irreducible if and only if f of x plus well, I'll just say this in this is more general, but f of x plus 1 is irreducible. Okay, so you can shift the coefficient. Okay, and now if we do f of x plus 1, right? So this is x plus 1 squared plus x plus 1 plus 1. So this is x squared plus 2x plus 1 plus x plus 1 plus 1. Okay, so this is now x squared plus 3x plus 3. Okay, now this polynomial is Eisenstein. This shifted polynomial is Eisenstein.
Excuse me, how would you know right off the bat that your shift would cause the polynomial to be Eisenstein?
You don't. I didn't. I know this one. So like, I tried shifting by 2. So one thing that you can see, it's hard to see. Yeah, I mean, shifting by 1 works a lot of the time. I don't know. The answer is I don't know. I mean, I tested some things out before doing this one. Yeah. Okay. So
have you noticed any trends at all? That, I mean, you kind of started to say something, but then said it might be a bit too tough to talk about. Are there any general trends for a good number to pick?
Theorems where you use like the binomial. So sometimes you have to use. There's a theorem that is a useful theorem, right? Is that okay? So it is P divides P choose J for J not equal to 0 and P, right? You know, and so this thing here is P factorial over P minus J factorial J factorial, and so this can be used. So this is sometimes useful. So, for example, I think you need this in one of the homework problems.
I'm guessing it's probably easy to get a computer to shift over by a number too, right? Trying things out, or
yeah, I don't. So a good question is, and I don't know the answer to this, is if a polynomial is irreducible over the integers. So here's a good question that I don't know the answer to, is that if is irreducible, does there exist some n in the integers such that f of x plus n satisfies Eisenstein? So this is essentially the question you guys are asking, and I don't know the answer to this question. And I actually don't know how hard this is. I do know that there are some super hard questions that are around this sort of thing, right? So like an open problem. All right, let me give you. Let's do a slightly easier one, and then I'll give you an open problem. Okay. Okay. So. Okay.
I'm sorry. Another question. How do we know this fact? Like, where does this fact about the shifting come from?
Oh, okay. So I can prove that one, right? So that's really quick. So let's see. So yeah, so let's do this shifting fact over here. Yeah, so the shifting fact is just really straightforward, right? So like f of x is equal to g of x h of x. Well, you know, f of x plus 1. Okay, so let's just do it this way. Okay, let's do it this way. This one. So this implies that f of x plus 1 is equal to g of x plus 1, h of x plus 1. Conversely, right, if I have f of x plus 1 is equal to g of x, h of x, right, well, this implies that f of x is equal to g of x minus 1, h of x minus 1, right? So if you have a factorization here, you have a factorization here, and if you have a factorization, you see what I'm saying? You can change out factorizations like this. I mean, and then you don't need to do this. You could this applies. This proof applies more generally. So replace 1 with a. Okay, and then you could do this. This doesn't even have to apply over the integers, right? And replace z with any ring, and the same idea holds. Okay, so this is Eisenstein, right? So so 3 divides the A0, right? But 3 squared does not divide A0. 3 divides A1, and 3 does not divide A2, where this is A0, A1, A2. Okay, here's a quick question. What if we had, let's do another example, just for like sanity. So what if I had the same thing, but I did x cubed plus 3x plus 3? Does this work? Yes, it still works. Yes, right? So 3 divides 0. 3 divides A0. 3 squared does not divide A0. 3 divides A1. 3 divides A2. And 3 does not divide A3. So this is still irreducible. So you can have 0 coefficients. Okay, so let's see if I have another one. So let's see what we did. So I mean, you could do the same thing, right? I just want to point out that you can do the same thing with y's, right? So if I did g of xy, if I did this is x cubed plus xy plus y in c of xy is irreducible, right? So here, you know, so A0. So you view as a polynomial in X. Of cy of X. So A0 is Y. A1 is Y. And A2 is 0. And A3 is 1. Right? So so Y divides A0, and Y squared does not divide A0. Y divides A1. Y divides A2, and Y does not divide A3. Okay, so we check this one again. All right, so that's all I really have to say about irreducibility. Oh, open problem, right? Okay, so here's an open problem. Okay, so let n be an integer, well, positive integer, greater than or equal to, I don't know, 2. Okay, so for which, let's do it like this. So let fn of x be x plus 1 to the n minus x to the n minus 1 over x. Okay, so for which n? And view this as a polynomial in z of x. So this thing actually has, if you expand this out, it'll have integer coefficients, because so this thing will have integer coefficients. So for which n is this irreducible? Right, and so I think this is a super hard problem, right? Yeah, and I think people don't know the answer to this. So, yeah.
Taylor, is it hard just because we don't really have like tools?
Yeah, it's hard because we don't have tools. Like these are our tools. I mean, there's some more sophisticated tools than what I'm saying because we have ways of dealing with prime ideals. But yeah,
But
it's hard.
not enough that.
There's no way to get our hands on it. Yeah.
Taylor, I might just be bad at math, but if n's equal to 1, how do we get integer coefficients? Like,
For n, for n is equal to 1, then this is 0, right?
oh, there we go. All right, that makes sense. Yeah. All right, I can't add that.
Yeah. For n is equal to 1, right? This is f1 of x is 0. Okay. But in general, so what does this thing look like? So. Well, let me do this after. Let me stop now, and then if people have to go, they have to go. And then I'll work this out after class.
Cool.